Everybody, Thrasher here. We are getting into something known as the law of universal gravitation. This is a law that Isaac Newton came up with, and we also learned some of the earlier laws from Newton. This is also sometimes known as Newton's fourth law, but it's a law dealing with gravity, something that we're familiar with, at least experiencing from the everyday. We're going to see there's an equation related to it, and at the end of the video, we're going to do one example by employing our proportion style of problem solving, okay? Now, gravity, when we talk about the law of universal gravitation, it sounds like what you think of, okay? The reason why you are staying in your chair right now, the reason why you're not floating in the air, the reason why an apple falls, the reason why the moon is sticking around by the earth is because there's this thing known as gravity, and gravity pulls on things, okay? The earth is pulling on the apple. We say it pulls to the ground. Technically, it's pulling to the center of the earth. Likewise, the earth is pulling on the moon. It's pulling the moon toward the center of the earth. It's a force because we learned that anytime you're pulling or pushing something, that is a force. So the law of universal gravitation, it has to do with a force, okay? The force of gravity attracts things. Again, probably not super shocking to you based on your everyday life. You wouldn't expect something to repel away from the earth because gravity is always an attractive force. It brings things toward one another. Okay, we know the feeling of the earth pulling things towards it. Now, Newton figured out that it's not actually just about the earth. Newton figured out that this is a force based on the mass of objects, any objects, and the distance, how far away those objects are. That's what this force is dependent upon. We experience the force from the earth more than anything because the earth is so gargantuan compared to all the other objects, but Newton found that really it's a force between all objects with mass based on how massive they are, and again, that distance, how far away they are. That's what this last little bullet point here says. It's a force between objects with mass. That leads to some weird things that you may not have thought about. This is going to be a silly sentence. You are physically attracted to other people. I say that because you have mass. Any other person has mass, and if you're standing, let's say, a certain distance away, that means there is a force of gravity. Now, that force of gravity is teeny tiny. It's microscopic compared to the force of gravity from the earth. You do not feel an attractive force to another person. Likewise, there is technically a gravitational force between you and your desk or you and your smartphone, but they're teeny tiny. I saw somewhere that the force of attraction between like two people is less than the weight of an eyelash. I'm not sure how accurate that number is. I didn't do the math, but it's so small we don't notice it. What we do notice is the gravitational attraction from the earth, again, because the earth has so much mass, we can really feel that effect. Now, the thing about the force of gravity is it's weird. Every force that we've gone over officially in notes, or probably any force that we've talked about if you're in my own class, it requires objects touching one another. It's been requiring contact. I took these images from some of my older videos. It also is true for things like pulling things with a string or a rope, okay, supporting objects. All of these examples that we saw, whether it was normal force or tension force, it deals with one thing hitting another, one thing contacting or pushing on or touching something else. But gravity doesn't require this contact. That's a bit odd. We say that gravity acts at a distance. Now, it might not feel odd just because you're so familiar with the force of gravity. I don't know if you can see, I'm holding up an eraser. You know that if I let go of an eraser, it falls down. It feels a force downward. But the earth wasn't touching the eraser. It was still able to apply that force. A silly example maybe is Star Wars. In Star Wars, the Jedi have this force. They can move things without touching. It looks cool on the the movie screen, but it's actually very similar to gravity. Gravity will move things even if it's not touching. It turns out that that's fairly rare. Most forces require there being contact between them, okay? Interesting, all right? Now, here's those same two diagrams, just again illustrating that even though the Earth isn't touching the apple or the Earth is not touching the moon, there is no contact required for those things. But getting to the heart of it, Isaac Newton found that there is this force we call the force of gravity. It is an attractive force, and it's based on objects with mass. So this is a very general diagram. This could represent the Earth and the Moon. It could represent the Earth and you. It could be the Sun and Jupiter, any two objects. So we have the mass of two objects. We'll just use them as or leave them as circles to keep it simple. Whatever the mass is, however far apart they are, there is a force of gravity acting on them. This is what Newton came up with. He came up with a relationship, a proportion. What he found was how strong this force due to gravity is, F little g, it is proportional to, it's related. We've seen this symbol before. It's related to the mass divided by the distance. Distance is in the denominator and the distance is being squared. This is what Newton came up with. It actually took about 100 years later for this relationship to turn into an equation. Another guy, usually attributed to a guy named Cavendish, he came up with the equation, okay? But it's the same idea. The force of gravity, it's based on the mass of two objects divided by distance. Gravity is always between two objects, but those two objects do not have to be touching, okay? We already learned that mass, we use kilograms. Distance, we are going to use meters. When we're dealing with astronomy, these can be very large numbers, but we are going to stick with meters. What's new and what's not in this is what actually Isaac Newton could not come up with. There is this constant called G. G, uppercase G, is known as the Universal Gravitational Constant. It's just a number. So there's not like another variable or something that's unknown. You're always going to plug in this number, 6.67 times 10 to the negative 11. Sorry if my head is in the way a little bit, okay? This number, the way you can think about it is like it's a multiplier. Like this is a force in our universe, but it was humans that came up with measuring mass in kilograms and us measuring distance in meters. The universe doesn't care about what little humans did. This is like how we change the measurements that humans make and turn it into a force that the universe is applying. In fact, if we use numbers or measurements other than meters and kilograms, we would use a different value for G. But we're not going to do that. In this class, if you are using this equation to calculate forces, we're always going to use 6.67 times 10 to the negative 11. It's a number that's going to be given to you, okay? Now, if you thought, I thought we already did this in a prior video, in prior notes when we learned about weight, and you're absolutely right. We already talked about the gravitational force. We often call it the weight. How much you weigh is how much gravity is pulling you down with. We even learned an equation for weight, W equals mg. But here's the thing. This is kind of a weakling equation. This is a simplification purely only for objects that are on planet Earth, near the surface of Earth, okay? Even in like skyscrapers, that still counts. But this equation doesn't work, I should say, when we're up in outer space. It doesn't work for Jupiter. It doesn't work for other galaxies. So while we did learn a version of the force of gravity, it was a much more simplified version. This, the universal gravitational force, this new one, this can be used for any two objects anywhere in the universe. It is a much more powerful, it's a much stronger equation. So this can be used anywhere. This is only to find the weight of things on planet Earth, okay? My last thing, let's do a practice with our proportions, okay? Yes, we'll do some problems where you are given a number for the mass m1 and m2, you're given a number for distance. Again, g is a constant, but we can also do those proportion style of problems, okay? So let's do it. Let's do a proportion problem. It says the moon feels a certain gravitational force from the Earth. So we got the Earth, we have the Earth, we have the moon, there's a certain gravitational force. The question is asking, what happens to that force if the moon was twice the distance away? Okay, that's what we're going to do. How does that force change? We'll assume that everything else stays the same. So remember, g is a constant. It does not change. We'll say the mass of the Earth isn't changing. The mass of the moon isn't changing. But according to the problem, the distance doubles. Instead of d, we're going to write 2d. Okay, you could try this on your own if you like. Or, of course, you could follow along or check the video to check your work. Okay? How do I like to solve these? The first thing I do is I write out the original. Here's the original formula, the original equation or relation. The force of gravity is equal to G m1 m2 divided by d squared. Now, let's rewrite it and let's put in the change. Notice, I still have Fg, I still have the equal sign, I still have G m1 and m2, I still have d squared, but because it says in the problem I'm going twice the distance, instead of d squared, it's 2d squared. The square is for the distance, so that's why I put parentheses here. Because I'm doubling the distance, I have to include that in my square. Now let's just do some algebra simplification, okay? The top doesn't change. There's a big hint. The top part isn't going to change, but what do you think I'm going to write on the bottom here? What's the next step? Remember, we've seen this before. The rule of math is if I'm raising something to an exponent, I have to do that for everything within the parentheses. So I have to take 2 and I have to square that. 2 squared is 4. D squared, well, that's just d squared. So notice, again, the top hasn't changed, oops, but on the bottom, I've now simplified this exponent here, okay? 2 squared is 4, d squared is d squared. So that's what I got. I'm going to do one more step, and I'm going to move over to the right just to give myself a little more room. Again, this is maybe kind of optional. I just want to show you this where I'm dividing by 4. It's the same thing as like if I pulled out, if I factored out that 1/4. This dividing by 4, it's the same thing mathematically as multiplying by 1/4. It's the same thing. So, what's the answer? What happens to the force of gravity if I've doubled the distance? You could compare the equations. In this one, the original, I have g m m d squared. In the new one, let's look. The same thing, g m m over d squared. What is different in this equation? The difference is I have 1/4. Or you could look down here. What's the difference? I'm dividing by 4. That's the difference. So how would you answer this question? The force of gravity is 1/4 times as much. Or you could say the force of gravity is 4 times smaller. So maybe this problem isn't as difficult as like the Kepler's third law problem, but we have to keep track of both if things are in the denominator and also in this equation there is an exponent, at least in one of the terms. But again, what's our process? We write out the original, we kind of put in the change, we do a little algebra simplifying, and then you really just try to look at what's different. Look at the original, what's different in our new version, and that's what the answer is for how the thing is changing, okay? All right, thanks a lot for watching this video on the force of gravity. See you next time.